want to see the other side now? Right. Okay, good afternoon. $50 SAT. I'll answer the obvious question that's going to be asked first. Did it cost $50? Well, no, it didn't. We forgot to include the price of the solar panels, which you can see there. They are quite expensive, and the total cost ended up being slightly less than $200. Right. 21st of November 2013 at 7:11, Dombrovsky Air Base. Dnieper takes off with 32 other satellites, including FunCube. The first 4 pocket cubes ever, which were Cube Scout Wren, Eagle 1, which was later called T-Logo Cube. That came out of Moorhead as well. And Eagle 2, which was $50 SAT. 3 hours later, those were due over the UK. And I was sat there listening in my clean room facility, 10:28, listening. And at 10:28, I heard some very strong Morse signals and managed to decode. Whoops, wrong way. Managed to decode the first data we got back, FSK RTTY. At that point, I'd have to say I was amazed. We many times did not think that something as simple as this would work, but it did, and in fact it's still working. Well, it was yesterday. Right, so who was the $50 SAT team? There were 3 of us, really. Michael from the US, Howie from the US, myself. There was really a 4th member of the team, who was Professor Twiggs. This, after all, was his idea. Now, we're all electronics professionals. I play with computers all day these days, but back in the 80s, those of you who remember the BBC Micro, I was senior engineer at the company that were making it. Right. Pocket Cube concept. Where did it come from? Well, it was Professor Twiggs, he who came up with the original idea for CubeSats. It was to be based on a 50 mim cube format, and in much the same way as you have 1U, 2U, 3U CubeSats, the idea was that you could also do the same thing, but on a 50 mim cube format. These smaller satellites would therefore have much lower launch costs. In fact, at the moment, Professor Twiggs is working on an idea for actually packing 8 pocket cubes into a CubeSat, which would then be launched as a CubeSat. There were a lot of skeptics about pocket cubes, I'd have to admit. Many a time we were told this couldn't possibly work. But I think they've been proved wrong, because 2 of them did go operational, T-Logo Cube, as well as ours. And T-Logo Cube did actually achieve quite a lot. I'll mention more of that later. Pocket cubes were to be simple to build, to use off-the-shelf components. We ought to be able to go into Macklin and buy the bits. And this would allow the construction of operational satellites to be within the remit of schools and colleges. Okay. It had been decided to use a pickaxe. Now, that wasn't my idea, I'd have to admit. But at the time, around the beginning of 2012, I had been doing a lot of work. I fly model aeroplanes as a hobby, and I'd been doing a lot of work with the pickaxe and the RFM22 together on some lost model locators. And I think what somebody must have done is they must have, put $50 pickaxe and RFM22 into Google, and I think my name popped out. So I had a phone call, an email from the team, and said, "Oh, would I like to be involved?" And I said, "Oh, yes, please." So I got involved around the beginning of 2012, and the idea was that they were going to use a pickaxe. That, I believe, was Professor Twiggs' idea. The pickaxe is a PIC-based microcontroller with its own onboard firmware, which is particularly easy to program and particularly easy to understand. very popular in UK schools and to a limited extent in the States as well. They use them for teaching technology to 14, 15, 16, 17-year-olds, etc. Okay. We also wanted to avoid using any space-hardened parts, and we didn't. Right. What were the minimum requirements that we were working with? The first was a Morse beacon. We needed to know that it was alive. We needed to report on the battery status and charge status. All right. It had to be low power. There's not a lot of, if you have a look beside that, there's not a lot of space for solar panels on a 50mm cube. So the whole thing had to operate at very low power. And to meet standard operating requirements, we had to be able to turn it off remotely. And that was probably the biggest challenge. Making a Morse beacon in space is not particularly difficult. But actually being able to turn it off remotely, well, that's a different matter altogether. So we had to come up with a way of having an uplink. Now the minimum distance we needed, this went into a high orbit, 600 kilometers. Now they were going to use the RFM22. That is a 100 milliwatts FSK transmitter, and the manufacturers sell it saying it's got anything like a 1 kilometer, 2 kilometer range. We wanted 600 kilometers out of it, which is a big ask. You might think, well, why an RFM22 in the first place? Well, think about it. There's not many radios that are that small. There are space-rated radios out there, but they're A, expensive, and B, they're just too big. RFM22 is frequency agile, which is great, so you can use whatever frequency you're allocated. It does have a direct modulation mode. You can fool it into transmitting Morse. But its main purpose is it's a data packet handler. It deals with telemetry at anything from 1 kilobits to 250 kilobits per second. So it has some inbuilt firmware which deals with formatting packets and what have you. At this point, we sort of had a problem. We needed to prove to ourselves that we could actually uplink to it. And we needed some real information on how sensitive it was as a receiver. Because once it's up there, there's not much you can do. So we needed to know that's going to work. And I'm not blessed with a lab full of expensive equipment. I've got an oscilloscope. So what we did, we did the next best thing. We actually just used the countryside as our test bed. And fortunately in South Wales, I'm from Cardiff by the way, fortunately in South Wales we've got lots of hills and valleys, and here's one of them. And if you look at that little peak, that little mountain right in the centre, that's referred to as Caerphilly Mountain. My brother Neil is actually standing on there. You might just about see him. And he's holding a transmitter. And I'm sat here at Machen Mountain listening. And all we did was we programmed up an RFM22 to send packets, the packets we were trying to measure, in decreasing powers, start at 100 milliwatts, 50 milliwatts, 20 milliwatts, all the way down. And we could then measure at which point it stopped receiving packets. It was quite simple. So I would just sit there and it would say you would receive a packet at 100 milliwatts, 50 milliwatts, 20 milliwatts, 5 milliwatts, then it would stop. So we had a baseline for how sensitive it was. And because we knew how far it was, you could do some maths and work out how sensitive it was. Okay, but we were actually, that was 8 kilometers, and I was picking packets up at 25 milliwatts fairly reliably, and the odd one at about 10 milliwatts. Anyway, what we needed was a much longer test with less in between. I mean, the sheep were getting in the way. So I looked around on the map, and fortunately for Cardiff, it's got a nice flat thing right by it, which is called the Bristol Channel. And fortunately, there is a mountain at either end. So there's a hill just outside Cardiff, and there's the Mendips just outside, just below Bristol there. So one sunny day in September, was it? September, 2000 and 2012. My brother was sat on this hill in Cardiff, and I drove around to this hill in the Mendips, and we were going to see what was going to happen. Now, this area, incidentally, I'm not sure any of you realise, is quite well known for range testing. That blue line there was I think it must have been an amateur called Mr. Marconi in 1897, apparently. That's all. He didn't get much further than that. That was the Cyffili de Machen that you saw, the sheep, and that was Cardiff to the Mendips. Now, we got 100% of the packets at 100 milliwatts, so that was a good benchmark we could work with. 50% of them were arriving at 50 milliwatts, and about 10% at 25 milliwatts. So we used the figure 100%, 100 milliwatts, and we used the distance, and Howie did the maths. Incidentally, you could hear the Morse beacon at 1 milliwatt from that distance. That was the calculation that Howie came up with. You're not expected to read that, but basically what he said was that at 2,600 kilometers, we would need about 36 watts into a beam, a small Yagi, to be able to command the satellite. This proved to be fairly accurate, in fact. The figure I have in my head is that on one occasion I managed to uplink to $50 sat, 2,200 kilometers, about 22 watts into my quadrifilar helix. Okay, so at 90 degrees we would only need about a watt. Unfortunately, I've never actually tried it at such low power, but whatever. And based on this, we thought we had a viable communications link over the entire pass. So we were fulfilling the requirement to be able to turn it off. And we can turn off the transmissions and they won't start again unless we send another command to turn it back on. So that's that. Now, at this point, myself, Howie and Michael had just basically been assisting the project at Moorhead with advice and whatever, and myself and my brother had been running around the hills and the valleys of South Wales doing testing, and we were just feeding the results back into Moorhead. But one fateful day, it was September, again around September 2012, there was a conference with Prof Twigs online, and he said, could you build a satellite? And we said, yeah, probably. And he said, right, if you have it ready in 2 months, you can launch it. Oh, great, we thought. So he offered us a launch slot, and we got to business. Now, the thing we did from the start was we decided to keep it extremely simple. And the reasoning behind this was, whilst there's an attraction to try and complicate things into advanced technology, we thought it was far more important to prove that a very simple satellite in this size and at this price point would actually work. So we really did keep it extremely simple, and we did the minimum possible while still fulfilling standard operating type stuff. We decided on 40mm boards. We had more space, and that's actually a working model of $50 sat. So we did have a bit more space, but we decided no, we're going to stick to 40mm because that's all that's available on a normal pocket tube. Got some water. We were going to use a pickaxe because most of the testing code I'd already done had been programmed in the pickaxe, and I didn't honestly see any reason to change. We had the conversation quite a few times throughout the project, and we said, well, it works, so why not? Just leave it, because it was quite reliable. Hold on. We were going to use the RFM22. Couldn't find anything else, suitable size. Besides, we had it working, and we did include watchdog and latch up protection. So it had most of the sort of standard things you might expect in a satellite. However, we had to put it all together, so it was my job to produce a development model, and this was done in the 50 sat clean room facility, which is my shed. You can see the QF helix at the top and the super amp. Very nice amplifier, those things. That is the development model, and it worked. And it was left outside for quite some time in the sun to prove it was all working. You can just see the battery in the bottom left there, a small lithium-ion battery. However, it's obvious you couldn't fly that. So the boards were designed, and there were two boards we required, and that's all we were going to do. There was a processor radio board, which was down to me, and we then needed a maximum power point tracker for the solar panels, and that was Howie's job. And these were done in fairly short order, within a month, I think, and we had them all working. That funny test lead thing is the programming lead. So we had those. We were going to use solar power. We were using task cells, those triangular things. There would be 4 panels and 3 pairs of task cells per panel in parallel. 2 task cells is just enough to charge a lithium-ion battery. You can charge it to about 4 volts, 4.1 volts just. We chose to charge the battery to 3.9 volts because we didn't have a clue as to how long it would last. Okay. 4 sets of task cells, LTC 3105 maximum power point tracker on the charger board. The charger board also had the current measuring capability. In order to run the latch-up protection, we needed to know how much current was flowing in $50 sat, and we could then force the power down if necessary. That was the current monitor. That was the battery. It's a tiny little thing. Got one somewhere. You can buy them on. There we are. You can buy them on eBay. They're about £2. There's the RFM22. So we then turned to what we were actually going to monitor and report on. What data we were going to get back. Voltages, obviously. We needed to know the battery voltage. We needed to know the solar power voltage, because this, again, nothing this small had been tried before. So we needed to know how the solar cells and stuff were performing. So we were getting voltages back, currents, both for how much power we were getting out of the solar panels, and for protection against latch-up, so we could deal with it if that ever happened. There was some thought that EEPROM would suffer corruption due to radiation particles, so we put in a test for an area of EEPROM to see if there was any corruption. We had the same thing for an area of the flash in the PIC microcontroller. Ran a check, and we did a SU-RAM check. There was a buffer area of buffer RAM which had a constant check for any bit flips. I'd have to say, to date, 8 months in orbit now, we haven't detected a single problem with corruption of data or whatever. It's been fairly reliable. One thing we had to I spent a lot of time doing is the RFM22. Whilst it's nice and cheap, it's about £3. It's got a very nasty habit of resetting itself. So we dealt with that, both in software and by some reasonable hardware design. Right. What communications? Morse call signs. Myself, Howie, Michael. It transmits our call signs in sequence. It transmits 50 sat. That's fixed. The 5th call sign is one of the ones we've been changing. We do it from the ground. It's been Professor Twiggs's, and I think it's currently putting out Moorhead Oscar 76. I think it's the last time I changed it. So we get Morse call signs, but the Morse is encoded in a special way. The frequency of the tone is actually directly proportional to the battery voltage. The speed of the Morse is directly related to the solar charge. So just by listening on a HT, you can tell what is happening in general. One side effect of this is because you can't charge lithium batteries below 0 degrees centigrade, charge is only turned on when it goes above 0 degrees centigrade. So in the UK, it wasn't until May that I heard the slow Morse beacon when the temperature of the satellite had risen above 0 degrees centigrade, to turn on the charge. And at the time I heard it, it was over Algiers. But it took till May. We'd played with fast Morse data. It worked. All it needed was a HT, an FL Digi, and a PC, and you could receive it. It's fairly reliable. So, for no other reason than it was working, we left it in. There's the 1 kilobits data telemetry, both up and down. It sends standard 1 kilobits data telemetry, and it then sends FEC encoded data packet as well. And of course the FSK RTTY. Now the FSK RTTY was probably the most inspired thing we did, I think, because it's proved to be a tremendous performer. It's only 100 milliwatts, but you pretty much get horizon to horizon coverage with it. You can I've picked up data on my QF Helix at 2,500 kilometers, and some of the other amateurs who've got tracking antenna arrays, they basically get it just as it comes over the horizon, so 3,000 kilometers or so. So it's been well. That was well worth adding. At this point, we more or less had everything working. We were quite happy. Somebody had to put it all together, and that fell to Michael Kirkhart in the US. And basically, all he did was take a series of aluminium plates and angles and put them together in a satellite. Now, the only critical component here is the base plate, which is E in that slide. That has to be accurate, because that is how it came out of the launch tube, which was called Mr. Fod. So that had to be fairly accurate. Apart from that, everything was completely non-critical. Now, there's a sequence here. It's a bit of a mismatch because it's to show how it was built. I've taken slides from Michael's construction of the flight model and the demo model, including that one that I've made. I've made another demo model, and Michael's made a demo model as well. So it's a bit of a mismatch of photographs, but it shows the sort of approximate sequence. Those are the side plates and the base plate prepared and ready. That's the base plate with the 2 launch switches added. There's the angle brackets going in. There you can see the PCB mount pillars and the brackets for holding the antenna. That's the battery, and the launch switch is wired in. Those are the boards in question being tested before we put them into the satellite. That's the antenna. Yes, it is steel tape rule on a bit of PCB. That's a choke balun for the dipole. That capped on tape was added because we had to meet a less than 25-year deorbit time. Bit of atmospheric drag. That's the antenna plate. That's Michael adding the wires for the solar panels. Yes, it is PTFE. That's sort of how we made the solar panels. Those little triangular things on a base plate and tapped wires. That's the solar panels themselves. That's it, more or less finished. That's a picture of the inside. There's quite a lot of spare space as it happens. That's me with my sophisticated sun simulator. That's the actual flight model. Michael just checking a few notes. I don't know if you can see that, but that's the flight model, 206. Is it 206 grams? Yes. This is the shake part of shake and vac. You obviously had to go through those tests, and that's a vacuum test. And everything was fine. At this point, it was actually hand carried from Moorhead to Italy, where it went into Unisat 5. That picture there was that's actually Cube Scout, we believe, being put into Unisat 5, which was the launch vehicle. That's at the University Roma in Italy, and from Italy it then went across to Russia. Meanwhile, I was working on the sophisticated command uplink system, and basically it involved remaking some stuff. Bear with me. Never mind.
About 5 minutes left.
Yeah, right. Yeah, that's about right. That's my sophisticated uplink kit, an RFM22 receiver, a kit amplifier from Mini Kits, which would boost. It's a good one because it'll accept an input of as low as about 10 milliwatts and amplify it up to about 35 watts. An antenna switch and a funky dongle. Few things we got wrong. The battery, well, not really, because there's not a lot we could do about it. There's very little information available on space-rated batteries in this size, so we just had to put up with it. There was some software errors, nothing of any significance, but it stopped us collecting some information on resets properly. We did have a problem with spin fading, we still do. You can hear when the FSK RTTY is running, it fades in and out sometimes. We should have paid more attention to spin fading. The time the satellite spends below 0 degrees centigrade is far longer than expected. It's about 15 minutes after it comes out of eclipse. It's still below 0 degrees centigrade. The temperature cycling regularly goes from -30 to +30 every orbit. There is no heating. Michael has pointed out that if we had paid more attention to actually making sure the solar panels were pointing at the sun, we would have got about twice as much power as we are getting. We're getting about 300 milliwatts at the most. We could have got about 585, we reckon, if we had made sure that as it went round, solar panels were pointing at the sun. What we got right? Well, it worked. We did keep it simple. We've been fairly open source about it. There's lots of stuff on the website. And this has helped us tremendously because the radio amateurs all over the world have been picking stuff, have been sending in telemetry reports. We did an awful lot of testing, especially the relationship between it operating in the sun and out of the sun. The FSK RTTY, godsend, that has been. The digital telemetry, I'll mention that right at the end. Right, final thanks. Professor Twiggs, of course, his project really. Moorhead University, they gave us some help with some of the testing and the solar panels. The Gauss Group, University of Roma, they were the UNISAT-5 guys. Chantal Capitelli, University of Brasilia. She was the lead there. All the radio amateurs there, including one M5AKA, who's been very helpful with communications with AMSAT for us. That's all. Oh, no, one next.
To say I was one of the skeptics.
There were many.
But I'm now convinced. I think that's fascinating. Thanks very much, Stuart. We are running a little bit over time, by about 10 minutes or so, but take a couple of questions if we've got some.
How do you handle that you have only a half duplex system? You have only a half duplex system, so you cannot transmit and receive at the same time. How would you handle transmitting?
Yes, it does. It's half duplex. It's one radio, so it doesn't do.
Yes, and if the transmitter is blocked, how do you unblock it?
I'm not sure what you mean.
So if it stays on transmitting?
Oh, I see. There's a timeout on that. Potentially the transmitter could stick on, but there is a software timing loop which says, hold on a minute, you haven't stopped transmitting, and it pulls it. We thought of that.
Okay, well then. Anything else?
Yeah. Because you have more space available, didn't you think about putting an additional battery, maybe?
We did think about it, but as I said in the presentation, we actually deliberately did not. We could have done, but we said no. We wanted to make sure that what we did would prove that it would work. So we deliberately avoided any unnecessary complication. But yes, there was plenty of space, and yes, there was an expansion bus, if you may have spotted it on the side of the PCB.
Okay, thanks very much. Well, let's show our appreciation to Stuart in the normal way. Thank you very much. I will be at the dinner, and this is a fully working model. One of the advantages of cheap satellites, you can make fully working.